Okay, so the only announcement I've got for today is the Chapter 21 sapling, which is going to be due 9 a.m. Wednesday because we finished that up last Wednesday. And I guess all you guys wrapped up the quiz for this week, so I'll be posting the key hopefully later today. I guess that's pretty much it for now. Any questions about that? Alrighty, cool. So last time, since we wrapped up Chapter 21, I've got the notes for Chapter 22 posted. So let's get straight into it. Okay, so the last three chapters that we did, 19, 20, 21, all involve stuff going on right at the carbonyl. So that might be in an aldehyde or a ketone, or it might be in some sort of carboxylic acid or derivative. But what we're going to be looking at in this chapter is something a little bit different. Still involves carbonyls, but it's not the same type of chemistry anymore. So we are now looking at enols and enolates. Okay, so the whole deal about this chapter is, if you keep this in mind, it'll make things like fit into a pattern a little bit more obviously. So these are reactions all involving the H that's one carbon away from the carbonyl. So in other words, these are all going to be called the alpha hydrogen or the alpha proton. Okay, so a really common theme that we're going to see here is we have some carbonyl thing, and it's got a bunch of H's on the carbons one away from the carbonyl. Turns out you can actually pull these off easier than you would expect for a carbon with an H on it, because if you have a base come in, pull that proton off, you can either show that charge going onto the carbon, in which case you can draw it like this form, which still doesn't look great for stability because, you know, negative charge on carbon has a pretty high pKa a lot of the time. The reason this one is so decent, it's still not great, but it's a lot better than it could be, is because of resonance. So we can show this thing kicking over. And if you look, this is that same 3-atom subunit that we're used to seeing in tons of resonance patterns everywhere. We've got 3 atoms in a group, 2 are double bonded, 1 has a charge of some kind, so we can swap which end is which. And draw it as that, which is looking much more stable than the C- version. Okay, so this thing is called an enolate. And you may be recognizing this functional group name, enols, because basically if we took this thing and stuck an H onto it, we would have an enol that has popped up in a few reactions before now. So it turns out we can actually do a lot of other useful chemistry too if we add some other reagents in while this is happening. So this whole chapter is about how to do chemistry at the carbon 1 atom away from the carbonyl. There's a ton of things that can happen there. Okay, so we might be seeing this in basic conditions, in which case it's probably going to go through the enolate. And then you're going to go attack something with enolate. Okay, so from here, you could show the attack happening 2 different ways. Oh, as a side note, I don't really care which resonance form you show it in. I guess left or right, which one do you expect to be the dominant form? Right, exactly, yeah. So this one's going to be the major form, but a lot of the chemistry and behavior that it does actually is a little bit more dictated by this form. So you can either show, when you're attacking with the enolate, you can either show the attack happening as if the minus charge were on the carbon all the time, in which case, whatever generic electrophile we're using, you just go straight in for the attack from there. Or you can show it attacking from this resonance form. You're still going to attack with this carbon. Like, we're not going to look at the few reactions that actually involve attack from the oxygen. And that's because for most of the electrophiles, we're going to see the bond strength of having a bond from a carbon to the electrophile ends up being more favorable than having an O to whatever electrophile. So we're always going to attack whatever else from the carbon. And so if you're showing it in what's actually the more sensible resonance form, you just have to do a little bit of extra arrow pushing to make that happen. So it's still this area that's going to do the attack, and the oxygen's kicking down to make that happen. So either way you show the key step of most of these reactions. You could show it this way, you could show it this way. It's still going to get you the same deal. In sapling, I think a lot of the time in the problem, they actually specify show your enolates with a negative charge on carbon. But if they don't tell you for a particular problem, I haven't actually gone through and checked all the problems for this chapter for this year yet. But if they don't specify, then you can show it either way, like on a test or something. I don't care which way you do it. So, okay, so that's kind of the gist of this chapter. Most of the reactions that we're going to see will be in base. In acid, we'll see a few in acidic conditions. We can't really make an enolate there because we can't have something with a minus charge floating around for long in acid. The general trend is we're going to make an enolate instead. Or not an enolate. We're going to make an enol instead. And so this is pretty much the reverse of the keto-enol tautomerism. We know that that generally favors the keto form, but it's in equilibrium, so there's always going to be like a little bit of the enol around. But so long as a little bit exists at a time, and so long as that little bit can go do some other reaction and get funneled over to some final product that we're trying to make, that turns out to be enough. It may just be a little bit slower while we're waiting on it to actually first make the enol form and then go do something. So, in other words, you're going to show exactly the reverse of acid-catalyzed keto-enol tautomerism, where we stick a proton on first, and then whatever neutral base, probably like water or an alcohol or something, is going to come deprotonate that and do like sort of an E2 looking thing here. And get you the enol that way, which can then go and attack things kind of like the enolate did up here. So if you bring an electrophile in at this point, the attack's going to look pretty much identical, except for the oxygen's neutral instead of negative. Yep?
Can you show an intermolecular proton? Like, do you just have an oxygen take that proton on the carbon, or is that?
For this one, I think no, because otherwise you wouldn't need to have the acid catalyst, I guess. So like if you already have like a surplus proton or a missing proton on the molecule, it makes more sense to show it. There might also be geometric constraints, but I'm not real sure about that. Yeah, good question though. Okay, so other questions about sort of these two options that we're going to be looking at a whole bunch of examples for. Okay. Cool. So a little bit of a reminder about keto-enol tautomerism. So the enol form is usually pretty disfavored. By a factor of about 10 to the 6th or 10 to the 7 for most standard ketones and aldehydes. But there are a few examples, or a few exceptions. So basically, if you give the molecule any really good reason to prefer doing the enol, for instance, it can achieve aromaticity that way, then it's going to strongly favor the enol. Or as it turns out, if you have one of these beta dicarbonyl things, we've seen some specific types of these, like beta keto acids, do decarboxylation, but this is going to be the case for any kind of beta dicarbonyl form. These will actually favor the enol form too, because if you make the enol on one side, then it can hydrogen bond onto itself. So sort of like we saw for the beginnings of decarboxylation, only because you don't actually have like another oxygen out here, you can never kick out CO2, and it's never going to go like anywhere from here. It just sort of sits in this hydrogen bond to itself state. Okay, so as kind of a general rule of thumb for this chapter, in base we're going through the enolate. In acid we're making the enol. We'll see a lot more enolates than enols because it's a little bit easier to set up the chemistry for enolates. Okay, questions about that? Okay, cool. All right, so the first thing we're going to look at here is actually something real simple, which is just proton exchange. Okay, so I guess no matter whether you're an acid or base, this thing is in equilibrium. The molecule is going to be all the time, like, have some chance of losing its alpha proton and then regaining it. But the thing is, when it regains the proton, it might end up looking a little bit different. So depending on how we set things up. So like this thing has 4 H's, 2 on this carbon and 2 on this carbon. If we put this into base and D2O, it turns out that over time, every single one of the alpha hydrogens is going to gradually get replaced with deuterium. And the same thing happens if we do it in acid too. So D3O plus. So acid or base, every single alpha hydrogen is gradually going to get pulled off. So it's the same reaction happening 4 times, but as sort of an example for how one step of this might look. So we pull off, maybe let's pick this alpha H out on the right. Pull off that. Make the enolate temporarily. And that could kick back down and take the H right back off of the base, which is also not impossible. But what's more likely is, since there's so much more D2O around, when it comes back down out of the enolate form, it's just going to rip a deuterium off of water. Okay, so that's how you get the first one on there. And then you just repeat that at random for any alpha hydrogen or deuterium, and eventually all four are going to get replaced. Okay. Questions about that? Yeah.
Sorry, why was the enol favored in the second example?
Oh, for this one? Yeah. So it's hydrogen bonding that is providing this one such a benefit. And this one doesn't favor the product by as much as over there, so maybe I should draw this arrow by like a little bit bigger. But it's enough that the enol form is still going to predominate over the keto form. Mm-hmm. Good question, thanks. Okay, so any questions about what's going on down here or any of the earlier stuff? Okay, cool. So this is usually not something that we do deliberately. It's just sort of a warning that all of these hydrogens, one away from the carbonyl, are not anywhere near as firmly attached as we might normally expect. Because they can come off relatively easily, they're always sort of in exchange with the protons in their environment. So if you put it in deuterium or D2O, you're going to be able to tell that eventually they'll all get replaced. Where it does actually cause significant problems is if you have a stereocenter at that carbon. Okay, so say you have a bold methyl group on there and a dashed hydrogen, and you put it in H2O with either acid or base, doesn't matter. So the exchange is going to happen just like normal out here. All of these H's will come off one at a time, get replaced with an H from water. You can't tell, it doesn't matter. But this H is also an alpha hydrogen. It can come off too. And so if we're showing this in base, for example, we're going to get to here. And note that as soon as we do that, we're turning this carbon from sp3 to sp2, which means we just lost all the stereochemistry we had there. So if we went to a lot of effort to make just this enantiomer of the molecule, we had better keep it away from any circumstances where it's going to make the enolate ever, because as soon as it does, we scramble all our stereochem there, and then when it comes back out, oh, I guess, we're going to have a racemic mixture now of both stereocenters there. Okay, so this actually happens in biochemistry a fair bit. There's any stereocenter one away from a carbonyl is going to get racemized once you put it in acidic or basic conditions. Okay, questions about that? Okay, cool. So both of these are not terribly useful. In fact, they're something that you would normally probably be trying to avoid, but they are something to be aware of. You're not really going to be able to accomplish much using these in synthesis, though. Okay, so the next reaction we're going to look at is actually super useful for synthesis. And this is alpha halogenation. Okay, so kind of like the name is hinting at, you're going to pull off an alpha H and add halogen there instead. Okay, so you can do this in either acid or base. In base it goes through the enolate, acid it goes through the enol, just like it says over there. So let's look at the acid version first, because it turns out there's an important difference between the two conditions that shows up here. Okay, so in acid, protonate the carbonyl, get to here, okay, so you got the enolates. All right, so that's the same as up there. Now what we've got is, oh, sorry, not the enolate. This is the enol. So we've got the enol. Now we can go attack an electrophile. And the electrophile that we're going to attack, so we want basically halogen that can have an attack done on it. Obviously having a halogen with a minus charge is not a good choice, because if we want to send in something with electrons to attack a halogen, we don't want it to be negative charged. The way we've gotten around this in the past, although we didn't specifically address it then, is by using a dihalogen. So in this case, if we attack this one and kick out the other one as a leaving group, we can treat this one like it's electrophilic, because this is a good thing to get attacked now. So we kick this down, we go attack one of the bromines, and we kick out the other one as the leaving group. Okay, so that gets us to here, and then you got a Br minus floating around, and you can show whatever coming in and deprotonating the carbonyl. Okay, cool. So that's done. All right, so we could go through this a second time, because we know like we can replace all of the alpha hydrogens in the molecule with deuterium, for example. So what if we try doing this a second time for halogens? So again, same kind of mechanism, but kind of a key, I guess like it goes through all the same steps, only the bromines already replaced one of the hydrogens by that point. But now we could do, you know, we've added sort of a second equivalent of bromine on here. Really, I guess you could even explain it using an earlier step. Okay, so let me actually draw out more details of this. Okay, so the same steps as above, just with a BR on there already. Okay. So this version with one bromine already on there versus this version that doesn't have any bromines on there, based on what we know of bromine's electron withdrawing effects, top or bottom, which one's going to be more stable? Top, yep. And so the first time through this reaction in acid is going to be more stable. Because of bromine's sort of inductively pulling electrons towards itself. and destabilizes the positive charge. And you can explain that in terms of this step versus up there, or you can explain it in terms of this step with 2 bromines versus up there with 1. Like any point where there's a positive charge on the molecule, more bromines is going to be worse for stability. So that's kind of why I drew out both options here. But either way you slice it, it's going to be slower the second time through. So in acid, you can actually stop this after a single addition fairly easily, just based on like stoichiometry and also like keeping an eye on monitoring the reaction. Okay. So overall, in acid, oh yeah, question.
I just have a quick question where the second BR would add on the same side as the original or the other side?
Good question. It could actually go for either, but either way, the bromine is going to be close enough, the one that's already on there, to destabilize the positive charge a little bit and slow things down. So yeah, I could have shown the bromine adding out on the left carbon too, and that would still be facing some issues. Okay, so overall in acid, we're just going to add 1 time. So overall reaction that we would show for this is H plus Br2 and you're just going to add a single bromine on there. And you can force it to overbrominate, I think, under pretty harsh long reaction times, but it's going to take some pushing. Okay, so in base, things are not going to be exactly the same. So in base, we're doing the enolate. So you get to here. Again, we still need to have an electrophilic bromine to go attack with the molecules, so we're still just going to use Br2 or, you know, whatever halogen 2. Okay, so now it's the enolate doing the attack. Okay, and that gets us to here. So if we try doing this a second time, and again, we could pick the left or the right side. I'll just stick to the right to keep it easier to follow. Okay, so again, we're going to make an enolate here. Okay, so top or bottom, which one is more stable? Bottom, yep, because now I'm trying to stabilize a minus charge instead of a plus charge up here in acid. And so here the bromine's actually helping because being electronegative, it's withdrawing some electron density. So this reaction is actually going to be faster the second time through, which means we have kind of a runaway reaction problem on our hands where you add once and then depending on stoichiometry, unless you're sort of careful about it, it may just keep adding multiple times. Okay. So it's actually difficult to make this thing stop after just one addition, in other words. Okay, so there's actually one interesting sort of carried to extremes version of this reaction. and that is if one group attached to the carbonyl is a CH3 group. In other words, we have some kind of methyl ketone under the old non-IUPAC naming. Okay, so say we've got some kind of methyl ketone going on here. We hit this with water, base, and Br2. It's going to go through this mechanism 3 times in a row. It might also do it for this R group out here, but because I'm leaving vague exactly what this is, let's not pay too much attention to what's happening out here. Let's focus just on the methyl group for now. So you pretty much do this reaction 3 times, and you get to CBr3. All right, so that's pretty much in line with what we just covered. Now something really weird happens, and that is that turns out this is actually not a terrible leaving group. It's got 3 halogens on there that actually all help to stabilize the negative charge. So it's a decent leaving group, which means we just turn this into something that's going to act kind of like an acid derivative in terms of you've got a carbonyl attached to something that can leave relatively easily. So from here, what's actually going to happen is something that looks kind of like hydrolysis of an acid derivative, where I know we said that we were mostly done with this stuff from the last few chapters, but at this point you're going to do more like an acyl substitution. Kick that down, boot out the carbon, get to here, and then because we're in base and we have a carboxylic acid, and we also just kicked out this thing, it's still fairly basic. I don't actually know what its pKa is about, but strong enough to do this anyway. So we're actually going to lose overall 1 carbon from the molecule and make a new molecule of this trihalo thing that we just kicked out. So okay. So as a category, this group of molecules, anything with a carbon with a single H and 3 halogens on it, are called haloforms. So the one you're probably most familiar with is chloroform, which is HCCl3, or deuterochloroform, which is DCCl3. But you can do this with any halogen. You can do it with bromine, chlorine, iodine. Not sure about fluorine, but this is actually a really good way. So I covered the Tollens test a few chapters ago, sort of an old way of telling, do you have an aldehyde in your molecule, a qualitative test for a particular type of functional group. And this is another one that used to be pretty heavily used to detect, do you have a methyl ketone in your molecule? So this is the haloform reaction, or the haloform test. For methyl ketones. So the way they used to do this is, it turns out both bromoform and chloroform are clear liquids that you can't really see that easily. But it turns out iodoform, so HCI3, is a yellow powder. And so if you do this reaction with some unknown ketone, and you use iodine as your halogen, and you get a yellow precipitate coming out of the reaction, then that tells you that your unknown ketone, whatever it is, one side of it must be a methyl group. So long before NMR got standardized and people had a much easier way of telling what their molecules look like, this was one way of figuring out exactly what was going on structure-wise, because it's a pretty easy way to tell, all right, if I'm getting a particular color of powder, like just coming out of solution when I do this, I must have had a methyl ketone in there. Okay. So the haloform test in particular is with iodine, but overall, this is just called the haloform reaction, and it's a convenient way in synthesis for getting a single carbon off of your molecule. Okay, questions about that? Yeah. So then it turns out, good question. So if it were an ethyl instead of a methyl, we do the same reaction and we get to here, but it turns out without the third halogen on there, it's not as good a leaving group and it's not favorable for it to get kicked out, so then it just kind of stops there. So then it's pretty much like the same as what we were doing over here with just keeping the molecule intact and just sticking some halogens on there. So, okay. Okay, so yeah.
So in acidic and basic conditions, how do we, like, will there be byproduct of the OH attacking the ketone directly and same with the water attacking the protonated ketone?
Yep, yeah, so that's always going to happen like in equilibrium, like is whenever you have a ketone around an acid or base, it's always going to make the hydrate some of the time, but it's reversible and usually favors the ketone for like equilibrium wise, so we're just kind of not bothering going into the details of what it's getting up to when the main reaction's over. Yep. Okay. Other questions about that? Yeah.
Is it possible if that R group that you drew up there with the methyl, that R group was also a methyl?
Good question. So if the R group were also a methyl, would you kick out two equivalents of haloform? I think so. I'm not sure like how much having this one O minus out here destabilizes the loss of the other R group. Yeah, I'm gonna have to look that up. Sorry. Yeah, but, good question though. I think I've only ever seen it happen to one side at a time, so it must be like the other oxygen kind of limits your ability to make enols or enolates out on this side once it's done. Okay. So any other questions about this reaction? Okay, cool. Okay, so one last variation of this that we're going to see. Oh, I guess this actually sort of indirectly answers your question. Okay, so one more complicated version. This reaction turns out to be not super favorable on things with carboxylic acids. Okay. So, the reason for that is both basic conditions. Base is obviously not going to make the enolate, it's just going to deprotonate the acid. And it turns out in acidic conditions, the enol is just not favored enough. Okay, so you can't throw a carboxylic acid into either like aqueous acid or aqueous base and expect this reaction to work. So instead, the workaround is we're sort of going to set up conditions that temporarily make an acid halide, and that can do the enol just fine. And then we're going to halogenate and then convert it back to the acid. So okay, so this whole combination of steps, which I'll drop in just a second here, has a particular name because it took some work to figure out how to get this to happen. This is called HVZ, which is named after Hell, Volhard, and Zielinski. Everyone just calls it HVZ because it's a lot shorter. So here's a carboxylic acid. We can't easily alpha halogenate out here the way we could for a ketone, but we can do something that we didn't even see at all in the acids chapter. We saw a bunch of acid chlorides. Turns out acid bromides are much more reactive still, which is why we don't really do much with them. They're too transient and short-lived. But if all you're doing is temporarily creating them so you can do something else on the molecule, turns out this actually works okay. So you can either bring in PBr3 and Br2, or you can actually, it turns out, just make PBr3 like in situ by adding just straight up phosphorus, which is very nasty stuff, and Br2, which combine to make the same stuff up here. So briefly, they will make the acid bromide. Very reactive. And then that will actually sufficiently form the enol that can then get halogenated at that position. Okay. And it only works well with Br. I'm actually not sure why chlorine isn't great for this. It might be because this is sort of a sweet spot in being like pretty reactive, but like still reasonable to form for short amounts of time. There might be something more to it than that though. Also, as kind of a point out thing here, remember how back in OChem 1, when we wanted to convert an alcohol into a bromide, we used PBr3? That's the same reagent we're going to be using here. Kind of like we can use SOCl2 to make either an alcohol into a chloride or to make an acid into an acid chloride. We can do pretty much PBr3, works on OH groups the same way. Okay, so from here, this is not going to sit around for very long because as soon as you expose it to any sort of water, including atmospheric moisture, that's going right back to the carboxylic acid. But if you're careful and you get in front of this thing and you trap it with some other sort of acid derivative kind of forming thing, so like we saw a bunch of this in the last chapter, say you throw in a molecule of alcohol instead, then you can actually get to the ester from that point, or you could do the amide perhaps. and make any other acid derivative depending on where you're headed here. Okay, so it's not going to sit around for long, but you can take advantage of it while it's there if you want, and not just go back to the acid, but tie in some other carboxylic acid derivative in the process too. Okay, so take-home message for this reaction is if you're trying to add some kind of small nucleophilic group here, I guess just like we saw back in OCHEM1, once you halogenate the alpha position, this is a convenient leaving group, and then you can swap it out for whatever other groups you want. So how much time I got left here? Okay, a couple minutes. So for example, we take this thing, we do Helvold-Zielinski to it, hit it with water, like this. But now we have some kind of convenient SN2able group going on this carbon, and if we want to swap it out for like any other nucleophile from our old alkyl halide stuff in OCHEM1, the example I have in the notes is like NaCN, but you get tons of options. Then you could, for example, swap that group in there to replace it. So once you get the bromine on there, you got a lot of places you can go with this, and assuming that this is an SN2 capable carbon. Okay, so that wraps up that section. Any questions about any of this? Yeah. There is, but yeah, so I think you would probably have to have like two equivalents of this, like one to get deprotonated, or one to deprotonate the acid and then one to do SN2. But as long as you're throwing in an excess, you're probably okay. Yeah, that and the HCN gas that you're taking out is probably not good, yeah. Okay.